Welcome. This is Professor Ridge and today's lesson on 5.1 Quadratic Functions. And today's first learning objective, recognize characteristics of parabolas. Recognizing characteristics of parabolas. The graph of a quadratic function is a U-shaped curve called a parabola. So as you can see in this figure, this is what we call a parabola, this U-shaped curve. That should look familiar to you. That's one of our basic toolkit functions of the square function, y equals x squared. That's been shifted to the right one, down 4. And we'll talk about that a little bit later. All right, one important feature of the graph is it has an extreme point called the vertex. So we call this bottom right here, in this case, the vertex. If the parabola opens up, as the one in this figure, that represents the lowest point of the graph or the minimum value of the quadratic function. So in this case, this parabola has a minimum value of -4, and it happens when x equals 1. So basically, since the parabola opens up, the minimum value is going to occur at the vertex, and it'll be the y value, which is -4. I don't know what happened to the negative on that. That's -4. All right. If a parabola, okay, I just said that. Oh no, I didn't. If the parabola opens downward or down, the vertex represents the highest point on the graph or the maximum value. So if we had a parabola that opened downward, then this point, whatever the y value for that point would be the max value of the graph. Okay? In either case, the vertex is the turning point. So we call this a turning point. Basically, when you have a hump, whether it's the peak or at the bottom of the valley. So the graph is decreasing, and at the vertex it stops decreasing, turns around, starts increasing, and then this is vice versa. So it's increasing till you hit that max value, then it decreases as you go to the right of that. Okay, so in either case, the vertex is the turning point in the graph. The graph is also symmetric with a vertical line drawn through the vertex, which we call the axis of symmetry. So this vertical line is what we call the axisymmetry. And then any point on the right side of this, like this point here, to -3, the mirror image or the symmetric point is this one. So basically, if you see that's 1 unit across, you go 1 unit across, and that's the mirror image point. Look at the x-intercepts here. This is 2 units this way, and then 2 units to the left is the mirror image. If you were to fold, if you had this graph on a piece of paper and folded it on that line, on the axisymmetry, the 2 halves would match up. And the y-intercept is the point at which the parabola crosses the y-axis. So you see that noted right here, y-intercept. So in this case, it'd be 0, -3. Okay, and that's standard. That's not just y-intercept is the point a graph crosses the y-axis. That's true for any graph, not just parabolas. And then same thing for the x-intercepts. It's the point, or in this case, the points which the parabola crosses the x-axis. So there's 2 x-intercepts in this case. So we have -1, 0, and 3, 0. If they exist, the x-intercepts represent the zeros. So that's a, I don't know if we've used this term before, but you'll hear that, zeros or roots of the quadratic function. The values of x at which y equals 0. So a 0 of a function is what x value makes the y value equal to 0. Okay, so for a parabola, the x-intercepts, the x-coordinates are the zeros of the function. Example 1, identify the characteristics of a parabola. Determine the vertex, the axisymmetry, zeros, and y-intercept of the parabola shown in figure 3. So here's our parabola. And okay, so we're going to start with the vertex. So remember, the vertex is that turning point It's the bottom if the parabola opens up, or it's the top if the parabola opens down. So that turning point right there, so that would be 3, 1. 3, 1. All right. Axis of symmetry. So that will be, now remember, axis symmetry is the vertical line that goes through the vertex. And let's change that to red. Okay, so that's the axis symmetry. And then if you recall from, I don't know if it was last section or a couple sections before that, we remember a vertical line is x equals, and then whatever the x coordinate it's going through. So it'll be x equals the x coordinate of the vertex. So x equals 3, which is that red line. Okay, so that's our axis of symmetry. And then let's see, zeros. Zeros are the x coordinate of the x-intercept. Well, in this case, there's none. So no zeros. Or I should say no real zeros. We'll learn about that later. So the x-intercept, the zeros are the real zeros are the x coordinates of the x-intercepts, but we're going to, if we did the quadratic formula, we can find the imaginary zeros. Okay, and then the next thing, y-intercept. So the y-intercept is where the graph crosses the y-axis. I'm just going to write y-int. So the y-intercept is 0, 7. Okay, so I think that's everything. So again, axis symmetry goes through the vertex, so x equals 3. This doesn't cross the x-axis, so there's no real zeros. Y-intercept crosses the y-axis at 7, so the y-intercept, remember the point, would be 0, 7. Our next learning objective, understand how the graph of a parabola is related to its quadratic function. Understanding how the graphs of parabolas are related to their quadratic function. So forms of quadratic function. I want to stop here and just mention, I would like you to make sure you read that section carefully. They do a pretty good job of explaining how they go about to get these forms. So anyway, so a quadratic function is a polynomial function of degree 2. The graph of quadratic function is a parabola. The general form of a quadratic function is f of x equals ax squared plus bx plus c. Some books refer to both of these forms as standard form. So this would be the standard form of when we get into polynomials, right? This is standard form of a polynomial in descending order. So that can be confusing. But if we're talking about, in this book, they're calling this the general form, okay, where a, b, and c are real numbers. And then the standard form of a quadratic function is written f of x is equal to a times the quantity of x minus h squared, the quantity squared, plus k, where a is not equal to 0. So in this bottom form, we can use our transformations on our basic toolkit function, the x squared, where we're going to shift it horizontally h units, vertically k units, and then a, if a is negative, it flips it upside down, and if a is the absolute value of a is greater than 1, it'll vertically stretch it, and if the absolute value of that's between 0 and 1, it would vertically compress it, right? So I'll show you when we get to graphing a few of those. Okay, so again, the vertex is going to get moved to hk, and if it's given in the general form, where it's just ax squared plus bx plus c, you can find the vertex to convert it to the standard form. By h will be just negative, or the opposite of b, over 2a. And then k, they kind of break down the formula in the textbook how to do it, but they say, hey, it's easier just to remember it's the output value when you put in the h. So figure out h, whatever that number is, plug it back into the function, work this out, and that'll be the y value for the vertex. So again, I would call this the shortcut to finding the vertex if it's given in the general form. And again, other books call this the standard form also. They actually, that's confusing a lot of people because both of these are referred to as standard form, but this book is making a distinction. So this one's calling that the general form and the other one the standard form. Example 2, writing the equation of a quadratic function from the graph. Write an equation for the quadratic function g in figure 7 as a transformation of f of x equals x squared, and then expand the formula and simplify terms to write the equation in general form. Okay, so here's the technique given over here, how to. So first when I identify the horizontal shift of the parabola, this value is h. Identify the vertical shift of the parabola, this value is k. So basically, you look at the vertex, and that's going to tell you where it shifts, right? That's your hk. So -2, -3. So we shifted to the left 2, down 3. So h is -2. So we're going to substitute those in the function. So f of x is equal to, oh, they wanted us to call it g of x, right? G. So g of x is equal to a, we haven't figured that out yet, x minus a -2, so that becomes +2. I'll just go ahead and write minus a -2 for right now. Remember that you switch the sign of whatever h is. So if this is +2, then this would be -2. So this would be +2. And then k is -3. Okay, so let's do this. X +2 squared -3. Now, you're going to substitute the values of any point other than the vertex on the graph of the parabola for x and f of x. In our case, it would be g of x. So let's see, here's a nice point. 0, 0, -1. So if we put in 0 for x and then -1 for the g of x, the y value, 0 + 2, and then we're going to solve this for a, and that's going to be our stretch factor, right? Or in this case, it'd be a compression, right? Because it's actually skinnier than the basic toolkit function. All right, so we're going to, let's see, 2 squared is 4, 0 + 2 is 2, 2 squared is 4, so we got 4a, -3, so I'm going to add 3 to both sides. So I'm doing a couple steps at once here. So add 3, that'll be 2, and then divide by 4. So a is 2 divided by 4 is just 1/2. Okay, so now we know a is 1/2. The absolute value of a is 1/2. And it's opening up, so it'll be positive. And now we can write our formula as g of x is equal to 1/2 x + 2 squared -3. Okay. And then they want us to go ahead and expand this so we can write it, the equation, in general form. So this is standard form. And then we're going to go ahead and multiply this out. So if you square, you want to do the square first. Here, let me circle that. Or box it. So this is our standard form. Now they want us to do general form, so you got to just multiply it out and simplify it. So we get 1/2 parenthesis Let's see. So we should do our square formula. Hopefully you're catching on to this, right? If I were to FOIL that, you get a squared plus ab twice, so it's 2ab plus b squared. Okay, so this would be x squared plus 2 times x times 2, which is 4x, plus 4, and minus 3. Distribute the 1/2. So we get 1/2 x squared plus 1/2 times 4 is 2x. 1/2 times 4 is 2. Okay, that's the end of the parenthesis. Minus 3. So then combine like terms. So combine like terms. We get 1/2 x squared plus 2x, and then 2 minus 3 is -1. So that is our general form. So all right. How to, given a quadratic function in general form, find the vertex of the parabola. So 1, you identify A, B, and C. Find H. So that's step 2. So the x-coordinate of the vertex, you find it by substituting A and B into this formula. H is equal to the opposite of B over 2A. And if you read the textbook, right, they showed you where that comes from. It's actually from the quadratic formula. The opposite of B plus or minus square root of b squared minus 4ac all over 2a. Well, if you're on the x-symmetry, you're right in the middle. And for the x-intercepts, if you go plus the square root and then minus the square root, if you're in the center, that square root part would be basically go away, and you're just at minus b over 2a. So that's kind of how I remember it. Or you can just straight memorize it. And then to find k, they also worked out a formula for it, but most people, including me, I don't try to memorize it. I just say, okay, once I know what the h is, what that x-coordinate is, I just plug it into the function and work it out, and then that gives me my k value. All right, so let me show you how I do it. All right, so our first step for example 3, find the vertex of the quadratic function f of x is equal to 2x squared minus 6x plus 7. Rewrite the quadratic in standard form, or vertex form. It's also referred to as vertex form. So we got the general form here. We're going to say, okay, a is 2, b is -6, c is 7, and then I'm going to find h for my the x-coordinate of my vertex is going to be opposite of b over 2a, which is the opposite of -6, or just 6, 2 times a. So we get 6 over 4, which is 2/3. Oops, I did that backwards. So I'm dividing both these by 2, so that'd be 3/2. I don't know why I said 2/3. Okay, so now that I got h, then I'm going to plug h into the function f. So k is just f of 3/2, which equals 2. So I'm taking all the x's out and put in 3/2 minus 6 times 3/2 plus 7. This will be my k value. So hopefully you have a calculator that does fractions, or if you're not good at them. I'll just go ahead and show you without a calculator. So when you square a fraction, you're going to square the top, square the bottom. So that's 9/4 minus, and then this, think of it 6 over 1. So 6 times 3 is 18 over 1 times 2 is 2. So we got 18 over 2, which is just 9. And then this will be 18 over 4 minus 2. And then 18 over 4, here, scratch work, let's see. 18 over 4 minus 2 over 1. We want to get a common denominator. So we're going to multiply top and bottom by 4. So that would be 2 times 4 is 8. And then they both have a common denominator of 4. So make it one fraction. Okay, so 18 minus 8 is 10 fourths. And then divide both those by 2. So you get 5 halves. So our k value is 5 halves. Okay, so now we know the vertex. Remember HK, we just figured it out. So the vertex is H is 3 halves, K is 5 halves. And then they want us to write it in standard form. So our standard form would be f of x is equal to a. A doesn't change, so a. And then x minus h, so x minus 3 halves, squared, plus k, which is 5 halves. And then that is our answer there, both of these. Okay, on to our next learning objective. Determine a quadratic function's minimum or maximum value. Finding the domain and range of a quadratic function. The domain of any quadratic function is all real numbers unless the context of the functions presents some restrictions. Okay, so in general, got a quadratic formula, the domain is just going to be all real numbers. Now the range of a quadratic function written in general form with a positive a value is f of x is greater than, so remember f of x is your output value, your y. So the range is the y values. So your y values are greater than or equal to f of negative b over 2a. So you look, basically this is the y value at the vertex. Or, so whatever that y value or k value is, greater than, you're going to be greater than that. So it's going to be from that value to infinity. The range of a quadratic function written in general form with a negative a is, and it's the other way around, so it's going to be, so basically that's a parabola that's opening down, and your domain, your range is going to be from negative infinity up to that k value of the vertex. Okay, the range of a quadratic function written in standard form, see this, you can kind of relate it, right? So basically, if you think of it this way, if we have a parabola that opens upward, right? We know that the vertex, this is going to be our max or min value. And that's the k value if it's written in the vertex form or standard form, or if it's the f of minus b over 2a if it's written in general form. Okay, so if this is the minimum value, the range is going to be from k to infinity, or if it's in the other form, it'd be f of opposite of b over 2a to infinity. Now if it's opening downward, it's the other way around. So the range is going to be, so if it's opening upward, range is going to be from k to infinity. And again, this would be your max value, which is your k of your vertex. So the range would be from negative infinity up to that max value. So it'd be negative infinity to the max value, which is k. And close bracket, right? So again, Your range starts here, and it's going to go up forever. That's going to be our range. Range is the y values. Okay, so given a quadratic function, find the domain and range. So identify the domain of any quadratic function as all real numbers. So unless something weird's going on, it's typically going to be all real numbers for the domain. Determine whether a is positive or negative. If a is positive, the parabola has a minimum, and if a is negative, the parabola has a maximum. Then determine the max or min value, k. If the parabola has a minimum, the range is given by k to infinity, and if parabola has a maximum, the range is given by negative infinity k. I like to just draw a quick picture, like I showed you in the diagram in the previous slide. Okay, so let's try this. Example 4, finding the domain and range of the quadratic function f of x is equal to negative 5x squared plus 9x minus 1. Since a is negative, right, a is negative, right, it's negative 5. This is a. This is a parabola that opens downward. If a is positive, it's a parabola that opens upward. So this, instead of, I don't memorize it up like it's written up there. I just kind of draw this picture. So it's negative, opens downward. So my range is going to be from negative infinity up to whatever this max value is. Okay, so it's going to be negative infinity to that max value. So now I just got to figure out what is that max value. Well, we know that we can find, if it's given in this form, the vertex is hk, where h is the minus b over 2a, and k is f of minus b over 2a. So I got to figure out what the x coordinate is, plug it into the function, and that'll give me that max value. All right, so a is negative 5, b is 9, and c is negative 1. We don't really need c for this. So we got minus 9 over 2 times minus 5, which is 9 over negative 9 over negative 10, which equals 9/10. Okay, now we're going to figure out k is f of 9/10, and then we just plug it into that formula. And again, if you have a calculator that does fractions, that makes it a lot easier. If you don't, you just got to go with it. 9/10 minus 1. So it'll be 81 over 100 plus 81 over 10 minus 1. So 5 times 81 would be negative 405. 81 minus 10 would be, okay, scratch work. I got negative 405. Let's see, 81, and then this would be 10/10. So I get 81 minus 10/10 would be 71/10. I want to get common denominators, so I'm going to multiply by 10, so I can just add a 0 at the end. And then 710 minus 405 would be, I don't have my calculator handy, so I'll just do it real quick. So it'd be 305. So 305 over 100, and then I can divide 5 out of both of those, I believe. So 305 divided by 5 would be 61. 100 divided by 5 would be 20. Okay, so we get, I'm just going to write the final answer there. So the max value is 61 over 20, which is like 3.05 or something like that. Oh yeah, because I had it in hundreds. 3.05. Okay, so then my range, so my domain, remember there's no funny business going here, so typically if it's a quadratic formula, your domain is going to be all real numbers, negative infinity to infinity, and the range, since this one was opening downward, it's going to be from negative infinity up to the max value, which we just found to be 61 over 20. Okay, and then that's our final answer there. Okay, so that's finding the max value so you can state the range. Now let's just do an example that says find the max or min. Okay, so before we do that example, I just want to highlight what the textbook put here. It's common for students when they give the max value or minimum value, they give me just the vertex, and that is not correct. Okay, the output of the quadratic function at the vertex is the max or min value of the function. So depending on if the parabola is opening upward or downward. So you can see in this one, if this parabola is opening upward, the vertex is 2, 1, but we would say that's the minimum value is 1. The minimum value of the function is 1. And it occurs or happens when or at, you can say either one, occurs at, happens when x is 2. Okay, so again, the max value or the min value is just the y coordinate of the vertex. Okay, so in this one, it's opening downward, and it has a maximum value of the y coordinate at the vertex. So the maximum value is 4. So you don't say it's the point, it's 4. And then if you want to say, okay, it occurs when x equals -3, that's fine. So again, just want to kind of say this a million times. The maximum value of the function is the y coordinate at the vertex if it's opening downward. And then the minimum value of the function, again, we're talking about quadratic functions. If we're doing other functions, it's different, right? Quadratic functions. So the minimum value is the y coordinate at the vertex. Okay? All right, now let's look at example 5. Finding the maximum value of a quadratic function. A backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. She has purchased 80 feet of wire fencing to enclose 3 sides, and she will use a section of her backyard fence as the 4th side. Find a formula for the area enclosed by the fence if the sides of the fencing perpendicular to the existing fence have length L. All right, so let's make a drawing. So let's say we have, here, let's make this a little bit nicer. Let's say I have, this is my fence, this line. Okay, so here's our fence in my backyard. And then I'm going to do a rectangular garden. And I'm only going to put wire on the 3 sides. And then we'll call this width. So they said that the sides, let's see, find a formula for area enclosed by a fence if the sides of the fencing perpendicular to the existing fence. So this is the existing fence. And then I'm going to put up wire on 3 sides to make a pin. Or what am I making? Rectangular space for a new garden that I'm going to fence in. Keep my dogs out of there. Okay, so area we know of a rectangle, or we should know, is length times width. We also know that we're going to put wire on these sides, and I have 80 feet of wire. So if I do, there's 2L plus 1W, because the fence was already here, so it's not going to be 2W, is going to be 80 feet. So this is for my wire, right? 2L plus W. And I want to write this as a function, find a formula for the area. So I just want to use one variable. So I'm going to solve this for W. So if I subtract 2L from both sides, W is 80 minus 2L. So now I can write my area as a function of L, where I have L times W, but W is 80 minus 2L. Then if I simplify that, I get 80L minus 2L squared by distributing it. And then let's put it in standard form or general form, plus 80L plus 0. Okay, so this is my quadratic equation in standard form, or general form, sorry. My other book called this standard form as well. So there's two types of standard form, depending on how you're thinking about if you're thinking it as a parabola, it would be that vertex form. And if you're thinking as a polynomial, then this would be the standard form. This book's calling it general form. So if you ever hear me refer to it wrong, that's why. Okay, so that's A. Now B, what dimensions should make the garden a maximum? Well, that's basically asking what's the maximum value of this parabola, and we know that this is a parabola that opens downward since A is -2, so that opens down. And then the y coordinate, that's going to give me my max value at the vertex. So I have to figure out the vertex. So h is minus b over 2a, which equals, so b is 80. 2 times -2. So that'd be -80 over -4, which is, let's see, what is that? 20? Now, I'm going to figure out K, which is f of 20, or I should say a of 20. A of 20. So a of 20 would be -2 times 20 squared plus 80 times 20, and then that would be, let's see, 400 or 4,000, I should say. Or is it 400? Yeah, 400, so -400, -800. And then this is 1,600. So 800 is my maximum area. Oh, that was not what they were asking for. What were they asking for? Let me go back and read the question. Got sidetracked here. What dimensions would make the maximize the enclosed area? So we didn't want to know what the maximum area is. We want to know what L and W are. Well, L is 20. So if L is 20, and then that one's 20. 20 plus 20 is 40. Plus another 40 would get me 80. So basically you just plug it in here. 80 minus 2 times 20. 80 minus 2 times 20. Or you can just reason through it like I was going to do. 80 minus 40 is 40. So that would be 40. So my dimensions that produces, so this is my answer for B. Dimensions that produces a maximum area are, what is it, 20 by 40. And you can see that makes 800 square feet. So it's 20 feet long by 40 feet wide. Okay, moving on to number 6, example 6, finding maximum revenue. The unit price of an item affects its supply and demand. That is, if the unit price goes up, the demand for the item will usually decrease. For example, a local newspaper currently has 84,000 subscribers at a quarterly charge of $30. Market research has suggested that if the owners raise the price to $32, they would lose 5,000 subscribers. Assuming the subscriptions are linearly related to the price, what price should the newspaper charge for a quarterly subscription to maximize their revenue? Okay, so the technique here, we're going to write a quadratic equation for the revenue function. And then we're going to find the vertex of the quadratic function and then determine the y value of the vertex. All right, so let's see here. So revenue is going to be the charge times, so if we do revenue as a function of x, it's going to be the price times the number of subscribers. Okay, so the price is, let's see here. Oh, we want to come up with an equation. See, market, it says linearly. So the number of subscriptions is related to price by, and they gave us 2 points. So they gave us 84,000 for $30. Okay, so $30. And then they also told us if it goes to $32, we're going to lose 5,000 subscribers. So that would be 79,000. So we want to get an equation to give us the number of subscribers based on the price. And then, so then we can plug it into this formula to get a revenue as a function of x. So x will be the price in this case, and y would be the number of subscribers. So our slope would be 84,000 minus 79,000. I guess I should have done it the other way, but it's okay. Just make sure you do it the same. So it's 84 minus 79, and then 30 minus 32. So that's fine. So this would be 5,000 divided by 2, negative 2, sorry. So it'll be negative 2,500 subscribers per dollar increase of the subscription. So now our formula for that will be the number of subscriptions we're calling that y, is equal to m, which is negative 2,500, x plus, now we got to figure out our y coordinate for this. So we plug in either one of these. Let's plug in the 30 and the 84,000. Oh, I did that backwards. This would be 84,000. And then this would be the 30. And that would be negative 75,000 plus B. Okay, and now just add 75,000 to both sides. So B is, what's that? 159,000. Okay, so now we have Y, which is the number of subs, written as a function of X, so negative. And again, it's a linear function because they told us, assume that it's linearly. Let's see, somewhere. Yeah, linearly related. So that's, we just do that process we did in the last chapter. X plus B is now the 159,000. Okay, so we're going to substitute this in for the number of subs. And then the price is going to be, what is the price going to be? Just X, right? So X was the price. So we created that function. And now we have this, if we, I should use a dot instead of times. Distribute that X, so we get negative 2,500 X squared plus 159,000 X. So that's our revenue as a function of X. And again, you can see it's a parabola that it's opening downward. So if we want to maximize revenue, we need to figure out the vertex, and it's the Y value. So again, max value is going to be the K. All right, so to find K, we need to know H first. So H is the minus B over 2A. So that'd be minus negative 2,500. You can just make that positive, right? It's the opposite of this. And then, oh, that's not B. Darn it. Minus B. So B is negative 159,000. B is 159,000 and the opposite of that. So it'll be negative. And then 2 times A is the 2,500. So whatever, let's see, this would be negative 159 over negative 5,000. So that will be 31.8. Right? So that's the optimum price to set is $31.80. Oh, that's what we want. So they're not asking us what our maximum. So it's always good to reread the question too. So it's usually that last sentence. Assuming subscriptions are linearly related to the price, which we figured out here, what price should the newspaper charge for a quarterly subscription to maximize the revenue? So the maximum revenue is the K value, but it occurs at the H value. So in this case, we're just looking for this number. What price should we set the subscription in order to maximize our revenue? Okay, so we should raise our subscription. No, we shouldn't raise it to $32. We should raise it to 31.8 if the research was correct, right? So this is our value we're looking for, 31.80. All right, so set our subscription price to $31.80 in order to maximize revenue. And then if you want to know what that maximum revenue would be, plug in the 31.80 into this function, and it'll give you a dollar value. Finding the x and y intercepts of a quadratic function, much as we did in the application problem above, we also need to find intercepts of quadratic equations for graphing parabolas. Recall that we find the y-intercept of a quadratic by evaluating the function at the input of 0. And again, that's for any function, not just parabolas. Okay, so we're going to set it equal to 0 and solve it for x, and that'll give us, oh, I'm sorry, we want the y-intercept. We're going to put in x equals 0, put the input 0, and find out what the y value is. Okay, now find the x-intercepts the other way around. You're going to set the equation equal to 0 and then solve it for x. Now notice in figure 13 that the number of x-intercepts can vary depending on the location of the graph. So for every quadratic function, it's going to have one y-intercept. So if you put in x equals 0 and then work it out, that's going to give you your y-intercept. Now for the x-intercept, you set it equal to 0 and solve it for x, and you can have the three possibilities here. You can have no solution to that. So if you have no solution, you'll have no x-intercept. If it has one solution, it'll be one x-intercept. And if it has two solutions, you'll get two x-intercepts. So depending on the parabola, you can get, when you set the equation equal to 0 and try to solve it for x, you can get 0, 1, or 2 solutions, which will give you no x-intercept, 1 x-intercept, or 2 x-intercept. Okay, so let's look at example 7, finding the y and the x-intercepts parabola. F of x equals 3x squared plus 5x minus 2. So again, to find the y-intercept, that's the easy one. Y-intercept. It's going to be, you put in 0 for x, and you plug it into the function and figure out what the y coordinate is. Okay, so if we do f of 0, plug 0 in for all the x's. If it's in this general form, it's real easy because basically the quadratic term, anything times 0 is 0, so that goes away. So 0 squared is 0, 5 times 0, still 0, minus 2, so the only thing left, that will be your y-intercept. If it's in the other form, that takes a little bit of work. Not much, but same idea. So our y-intercept is equal to 0, negative 2. Okay? So that's our y-intercept. Now for our x-intercept, you're going to find the zeros of the function. You're going to set the function equal to 0. So basically it's going to look like some number 0, and you can get more than one. You can get 0, 1, or 2 solutions for this. So we're going to set the function equal to 0 because we want the y value to be 0. So 3x squared plus 5x minus 2 equal to 0. Then we have to factor it. So hopefully, if you remember the factoring by grouping, here I'll do it in scratch work up here. 3x squared plus 5x minus 2. So I do 3 times 2 is 6. It's negative 6, but remember I don't worry about the negative. Factors of 6 that subtract to 5. So if I go through factors of 6, 1 and 6, 2 and 3, and that's it, this one subtracts to 5. So what I do is I'm going to rewrite that middle term as 6x and 1x minus 2, and the bigger of these two numbers gets this middle sign. So it'll be positive 6, negative 1 to get the 5x. Then I break it up in my two groups. I can pull a 3x out of the first group, x plus 2. I can pull a negative 1 out of the second group, x plus 2. And then I can factor out the x plus 2. And then what's left is the 3x minus 1. So hopefully you remember how to do that. If not, you can use the quadratic formula as well. Okay, so we have it factored equal to 0, and then we set each factor equal to 0. Oops, I don't know why I wrote 3. 0. So we're going to subtract 2, so x equals negative 2. And then on this one, you're going to add 1, so add 1, and then divide by 3. So x equals 1/3. So our x-intercepts are, we have two of them, negative 2, 0, and also 1/3, 0. So we have one y-intercept. You'll always get one y-intercept. For x-intercepts, you can get up to 2, 0, 1, or 2. Okay. Okay, here's the graph. So you can go to Desmos and graph it and verify that those are your x and y intercepts. The book gives a picture of the graph. And you can see negative 2, 0, 1/3, 0. Those are the x-intercepts like we found. And the y-intercept is 0, negative 2. Okay, let's look at another example. Find the x-intercepts quadratic function. F of x is equal to 2x squared plus 4x minus 4. And they're going to use a different technique. I don't know if I'm a fan of this technique, but I'm going to show it to you the way the book does it. So here's the technique. Given a quadratic function, find the x-intercepts by rewriting this in standard form. So they want you to first figure out what substitute a and b into the h equals the opposite of b over 2a. So we want to find the h. So h is going to be, so a is 2, b is 4, c is negative 4. Okay, so the opposite of b over 2a, so that's negative 1. And then k is f of negative 1, which is 2 times negative 1 squared plus 4 times negative 1 minus 4, which is, this is 1 times 2 minus 4 minus 4, which is negative 6. Okay, so now that we got h and k, then we can write it in standard, and a is 2, so that doesn't change. So now we can put it in the standard, the vertex form. So f of x is 2x minus h, so minus of minus 1 is plus 1, then minus 6, the plus k. Alright, so this is in the standard form. Now, solve for when the output of function would be 0, define the x-intercepts. So for our x-intercepts, see what I would do is I would just set this equal to 0 and use quadratic formula right out of the gate. So this book's just showing another technique. Again, I don't know if I'm a fan of this technique, but here it is, x-intercept. So what you do is we're going to set this equal to 0 and then solve it. Now, instead of multiplying this out, it's actually kind of easy to solve it from here if we use the way that we actually built the quadratic formula. Is you're going to add the 6. You want to get this square term all by itself. So you add 6. And again, like I said, I don't know if I'm a fan of this technique. If it's in this form, I'm going to use this technique. But so 6 divided by 2 is 3. But it seems like, you know, a little bit of extra work when I could just plug it in the quadratic formula. Okay. I've said that enough, I'm sure. Okay, so let's say I had it in this form already. Okay, then I want to get the square term, this x plus 1 squared all by itself, which I did. Now I just square root both sides. The square and square root cancel each other, and you get plus or minus square root of 3. And then you subtract 1 and just put it in front. So subtract 1 And then that'll be my two x-intercepts, the x-coordinates. So the x-intercepts will be -1 plus square root of 3, comma 0. And then -1 minus square root of 3, comma 0. Okay? So that's another way to do it. And personally, I don't care if you do it that way or just plug it in the quadratic formula. Okay, on to example 9, applying the vertex x and x-intercepts of a parabola. A ball is thrown upward from the top of a 40-foot building at a speed of 80 feet per second. The ball's height above ground can be modeled by this equation. H of t equals -16t squared plus 80t plus 40. A, when does the ball reach its maximum height? B, what is the maximum height of the ball? C, when does the ball hit the ground? Alright, so it seems like all the examples we did had a negative A. So this again is a parabola that's opening downward. And remember, we're having, this is, the y-coordinate is our height. And then the x-coordinate is our time. So we want to find, and this is not, to scale, it's just opening downward. So this will give us our maximum height. Max height. So we got to figure out the vertex. So again, if I do h for my vertex, so not this h, h for the vertex, h is equal to minus b over 2a, which is -80 over 2 times -16, and that is 2.5. So we just punch that in our calculator. Now be careful when if you go -80 divided by 2 times -16, make sure you probably need an extra parenthesis there, or it might give you a different answer. Alright, and then k would be h of the capital H for height of this h, which is t, 2.5. So -16, 2.5 squared plus 80 times 2.5 plus 40. So punch this in your calculator and you should get 140. And this is seconds, and this is feet. Okay, so that vertex is 2.5, 140. So the maximum height is the 140. Oh, it says when does it hit the maximum height? So that's the h part in 2.5 seconds. So 2.5 seconds. B, what is the maximum height? That's the y value, 140. And then C, when does the ball hit the ground? So we want to find the x-intercept. So remember, the x-intercept is when it's equal to 0. So we set the function equal to 0, and then figure out what the t value is. So let's see here. What can we factor out? We can factor out a -4 from all of those. So I get 4t squared plus 20t plus 10. Oh, I could have taken more. So I could have taken 8. So then that's going to give me 2, 10. Here, let me just rewrite it. So if I take out 8, I get 2. Oh, I'm taking out -8. So -10 and -5 equals 0. Factors 10, let's subtract to 10. And I don't think that's going to, I can do that. So I got to plug it into the, I can plug this into the quadratic formula so it doesn't factor. So let's just cross that one out and just plug this into the quadratic formula. So the opposite of b plus or minus square root of b squared minus 4ac all over 2a. And then you punch this all in your calculator, hit, and you got to do it twice. You do negative 80 plus square root of that mess, divided by, again, you probably need an extra set of parentheses, divided by negative 32, or just do that in your head. And you get negative, so the plus one, you're going to get about 5.458. And then the negative one, you're going to get about negative 0.458. And of course, we can't go back in time, so we're going to throw that one out. So it's just going to be, it's going to hit the ground 5.48 seconds after you throw it. Okay, and that brings us to the end of the lesson. So again, I want you to practice, practice, practice. So go to the end of the exercise, the section, and do as many of the odd exercises. Feel like you need to do more, do some of the even ones. All right, so I will see you next time.